All right, so we are here with our HonorStat students to talk about sampling distribution models for means, continuing our work that we started yesterday about these sampling distribution models. So in this slide, I introduced to you the fundamental theorem of the class you're taking. All right, it's called the central limit theorem. All right, and I briefly touched on this with proportions yesterday, but you're going to see today that we're going to make sampling distribution models based on population distributions for means that may or may not be unimodal and symmetric. And what the amazing thing about statistics is that it doesn't actually matter. Okay? These sampling distribution models for these sample means can still be approximated using the normal model as long as your sample size is large enough. All right? And the larger the sample size, the more confident you can be that it looks normal. All right? So you're going to hear that a lot over basically the next 4 months. So that's what's happening with the central limit theorem. All right. Now, if you were here yesterday or you watched the videos that I posted, you probably saw or you remember that we're going to have to make some assumptions. All right? What do you notice about these two assumptions? They're the same as the ones yesterday. All right? One is the independence assumption. All right? So the same thing as yesterday. And the other one, the sample size assumption, is also the same. So right now, there's no difference between yesterday and today, proportions and means. All right? So we're still going to make the same two assumptions with a sentence. And then you guys know that when we make those assumptions, what must we do after we make those assumptions? We have to check the conditions. All right, let's see who remembers the conditions from yesterday. Without looking, randomization and 10% condition go underneath independence. What was the one from yesterday that went underneath sample size assumption? Stop looking at your notes. Success, failure, condition. All right? So let's look at the conditions that we're going to do today. You're going to notice it's the same two for the independence assumption. We're going to have the randomization again, as well as the 10% condition. So we can do that one as well. Okay? See how those are the same? But instead of the success, failure condition, see what it looks like now. Now it's called the large enough sample condition. Now this one is one of those we're not going to be able to do much work, right? With success failure condition from yesterday, we did n times p and n times q. We're not going to be doing that. We don't have proportions, so those formulas are not applicable for means. All right, so really it's just going to be a sentence about thinking, is our sample size large enough? Okay, so the problem we do today, you'll see how I address that issue of not really knowing if it is large enough or not. Now, we're still going to be able to do the same work that we did in the 10% condition. Remember yesterday, I took the sample size and multiplied by 10 and asked myself, are there more than that many cars in the population? So it'll be something similar today. Now, we're going to do a lot of work with means, like I said, next unit, and you're going to see that we're going to actually use the Chromebooks and Desmos to make a sketch of what our sample looks like. And that will help us address some of the stuff later on in the future. Not today's class, because today we're still dealing with populations. Okay. Now, for the normal model, all right, remember we did this yesterday. When you have a normal model, you must have a mean and a standard deviation, or a mu and a sigma. Now, for the mean here, right, these are means, so we're just going to use the population mean. All right, that's mu. All right, but you'll notice we're not going to use sigma. Do you see how we're not going to use just sigma? We're going to take sigma, our population standard deviation, and divide it by the square root of the sample size. So that formula we used yesterday, remember that square root of PQ over N? That's not happening here because these are not proportions. Okay, so this is the formula we're going to use for our standard deviation for our model. Okay, almost there. All right, now this mentions that we're going to have two distributions to deal with, but ultimately we're going to focus here on the sampling distribution model for a sample mean. All right, and even though we don't know what our population mean is going to be, we're going to use our sample mean to estimate it. Okay, so we're going to still be able to make inferences and draw conclusions about the population even by only have run one sample. That's probably the most amazing thing about what we're able to do, is we can make these statements even though we've only done one sample. All right, so the last thing, really I want to just talk about this last piece, sampling variability. You're going to hear the term in statistics where someone will talk about sampling error, E-R-R-O-R, and that is not a bad thing, right? You guys, when you're young, you think when you see the word error that you made a mistake. But in statistics, when you have sampling error, that just means that you ran a sample, someone else did a sample, and you have different results. No one did anything wrong. You guys did everything right. You just have different results because you had different samples from that same population. All right, that's called sampling variability, and that is where pretty much all the work we're going to do for this semester lives in that sampling variability.